I'd like to give you an introduction now to atomic orbitals. We're familiar with hydrogen, and when we draw a very simple electron energy diagram for hydrogen, what we do is we have the nucleus here and we have a lone electron floating around the outside in some orbit. This is not really a true representation, but it is an approximate representation, and we can use this to approximate the Bohr orbit and say that it's n equals 1. When we're representing this as an orbital, though, we represent it as a line and we represent a single electron. Now, an orbital can have two electrons, and one would be up and one would be down. And if we're talking about the first Bohr orbit, then we represent this as being 1s, and we put a single electron in here. All right, let's look at what a 1s orbital actually is. And a 1s orbital represents the space or the area or the volume where we could expect to find that particular kind of electron. So this very electron here could be found in any area around the nucleus, and you'll see by the concentration of the dots here that we usually expect to find this particular electron at a space that was fairly close to the nucleus, and that's what all these little blue dots are. But you can see the electron could be found as far out as here, but not very often, but still could be. Now, the very shape of this area is spherical, and it would look like this. So this is the region where we could expect to possibly find that particular 1s electron, and that's in this shape or area right here. Now, if we take something a little bit more complicated, we take neon. And if we draw a very simple electron energy diagram, we would have a first row here that would have 2 electrons and a second row here that would have 8 electrons. The first row approximates out to n equals 1. That's our first Bohr orbit, and as I said before, we can have 2 electrons in that first orbit. In the second orbit, we can have, that's n equals 2, we can have a mixture of what we call 2s and 2p electrons. And again, these electrons will appear in specific regions that are going to be around the nucleus. So I want to show you what those look like. Let's first of all look at the 2s, and these spaces represent the areas where, again, we could expect to find the 2s electron. Let's look at the distribution with the electrons. Give it a second to come up. Alright, so again you can see that we've got 2 separate distinct areas, and we've got this region here called a nodal region. It's hard to see in this diagram, where you would actually expect to find no electrons. And these 2 different colors here are representative of what we call phases, and these phases are going to be useful when we talk about combining atomic orbitals. But for now, don't worry about them too much. They just still represent areas where we could expect to find the electrons, and we've got this nodal space in here, or this area where we don't expect to find electrons at all. And as we go up with the 2s, the 3s, the 4s, they have the same shape, but they increase with the number of these phases and nodal regions. Alright, let's take a look at the 2p. And the 2p consists of 3 separate orbitals, a pz, a px, and a py, each of them being along the z, x, and y axes respectively. And these again are areas where we expect to find these particular electrons. Let's take a look at what the distribution looks like. And there we go. This would be for the pz one. And you can see that we could expect to find electrons here and electrons down here, but again, no electrons in the actual plane here. So this is what the p orbital looks like. It looks like a dumbbell shape, and again, since we've got 3 axes, we can have 3 separate ways that this could be represented. And as you can see again with the p orbitals, we've got these 2 separate phases, and we've got a phase on top and a phase on the bottom. They're different colors, and again we'll use those when we talk about combining these atomic orbitals.